Arratsaldeon guztioi, Donostia International Physics Centerren izenean, ongi etorri Passion for Knowledge jaialdira. Ona, etorritako guztiei guri eskerrik beroenak.
Jaun Andreok, arratsaldeon.
Bienvenidas y bienvenidos a Passion for Knowledge, un festival cuyo objetivo es promocionar la ciencia como actividad clave para contribuir al bienestar de las generaciones venideras y celebrar la sede conocimiento como motor de progreso científico, tecnológico y cultural. Me hago eco de las palabras de Pedro Miguel Echenique, presidente del DIPC y de Passion for Knowledge, cuando reivindica que la ciencia es parte esencial de la cultura humana, probablemente la obra cultural colectiva más importante de la humanidad. Passion for Knowledge es, por ello, pasión por la cultura. A Passion for Knowledge acuden grandes figuras mundiales de las ciencias y de las humanidades de diferentes disciplinas, entre ellos varios premios Nobel. Pero, sobre todo, Passion for Knowledge reúne a la ciudadanía para compartir el conocimiento científico y fomentar la participación del público en la ciencia y sus valores. Como habéis visto en el vídeo, el extenso programa incluye, además de diversas conferencias plenarias, como las dos que tenemos programadas hoy aquí en Bilbao, tenemos también encuentros entre estudiantes de secundaria y científicos, exposiciones, talleres infantiles, espectáculos, proyecciones, etc. Esta es la quinta edición de este festival que arrancó en 2010 para celebrar el 10º aniversario del Donostia International Physics Center. La mayor parte de las actividades de Passion for Knowledge se celebran en la ciudad de Donostia San Sebastián, aunque uno de los retos del festival es extender su impacto más allá de su sede principal. Así, parte del programa de Passion for Knowledge tiene lugar aquí en Bilbao. Esta mañana, por ejemplo, se ha celebrado un encuentro de estudiantes de secundaria del País Vasco con varios de los ponentes de Passion for Knowledge, en concreto con Donna Strickland, Albert Firth y George Smoot, 3 premios Nobel de Física. El DIPC fue creado como una aventura intelectual. Toda aventura está animada por una pasión, en este caso el conocimiento, la curiosidad, el descubrimiento. De ahí el título del festival, Passion for Knowledge, y todo ello con un principio guía fundamental, la excelencia en todas sus actividades. Excelencia que es alto rendimiento, pero también y sobre todo rigor, responsabilidad e integridad. También el DIPC es una aventura institucional, un ejemplo de colaboración pública-privada gracias al compromiso de diversas entidades que han puesto y prestan su apoyo con determinación y continuidad. DIPCren izenean eskerrak eman nahi dizkiet patroi publikoei. Guri eskerrak beroenak Eusko Jaurlaritzari, Euskal Herriko Unibertsitateari, Gipuzkoako Foru Aldundiari eta Donostiako Udalari. Gracias también a los patronos privados, Kutxa, CAF, Telefónica y EDP Naturgas. Especialmente, hoy queremos dar las gracias a Telefónica por haber facilitado que este acto tenga lugar en un escenario tan privilegiado de la ciudad de Bilbao como es este Palacio de Euskalduna. Y sin más preámbulos, damos ya la bienvenida a la primera ponente de Passion for Knowledge en Bilbao, Francesca, la profesora Francesca Ferlaino. Francesca Ferlaino es napolitana y es experta en física cuántica. Su actividad investigadora más reciente explora fenómenos cuánticos en gases atómicos a temperaturas ultrabajas. Francesca y su equipo de investigación de la Universidad de Innsbruck, en Austria, recientemente marcaron un hito en la ciencia, el descubrimiento de un nuevo estado de la materia llamado supersólid, con propiedades sólidas y líquidas a la vez. Este fluido tiene la estructura de un cristal, pero las partículas que contiene fluyen como un líquido porque están deslocalizadas cuánticamente y son indistinguibles. Francesca Ferlaino estudió física en la Universidad Federico II de Nápoles. Recibió el doctorado en física en la Universidad de Florencia y en el Laboratorio Europeo de Espectroscopía No Lineal. En 2007 se trasladó a la Universidad de Innsbruck, en Austria, y desde 2014 es catedrática de dicha universidad y directora científica del Instituto de Óptica Cuántica e Información Cuántica de la Academia Austriaca de Ciencias. En los últimos años ha sido galardonada con numerosos premios y distinciones de prestigio, entre ellos el premio Erwin Schrödinger, el premio Feltrinelli a jóvenes investigadores, la cátedra Alexander von Humboldt, el premio de Ciencias de la ciudad de Innsbruck, el premio Ignaz Lieben y el premio Fritz Kohlrausch de Física Experimental. Además, ha recibido el premio START y 3 becas del European Research Council en sus modalidades de Starting, Consolidator y Advance. Francesca nos va a ofrecer una charla con un título muy sugerente: Átomos acercándose al cero absoluto de temperatura, el hardware de las futuras tecnologías cuánticas. Os puedo asegurar que Francesca es una gran científica y comunicadora, como vais a poder comprobar ahora. Tenemos la suerte de que suele venir mucho por el País Vasco, dentro del programa de investigadores e investigadoras visitantes del DIPC. Esperamos que algún día pueda compaginar su trabajo en Innsbruck con una dedicación parcial permanente entre nosotros en el DIPC. Ya tenemos la parte difícil de la ecuación resuelta, porque su marido es de Donostia. Ahora solo nos queda que nos considere a la altura de su excelente trayectoria científica. Profesora Ferlaino, the floor is yours.
Gracias y eskerikasco. I think I will do my talk in English. I hope it's fine. There is the translator. So it's a great honor to be here. It's a great honor to be part of this fantastic festival celebrating science and celebrating really the passion for knowledge. And I really think that this is a very deep feeling to have this passion. And when I've been invited, I had to choose what I will speak about. And so I thought that maybe the best to come together in this festival was showing what is the way that several quantum physicists have taken over the year, what is the feeling of a new discovery, what is the feeling of thinking about things which are very far away from our normal life. So I will just briefly mention at the end the research of my group, because I would like actually to bring you on a journey with me. The journey that is called, a word called quantum, and to try to explain what is going on now. And to do this, I think that I would like to start with a quotation, really celebrating this passion of knowledge. This is from Erwin Schrödinger, that was one of the founding fathers of quantum mechanics. And so what he's saying, and I think we should really take a few seconds to think about, is that the task of scientists is not to see what has never been seen before. Actually, the task is to think what have never been thought before. About what? About what is around us every day. So to think different. That's kind of the feeling, the message. What we see every day, but we think differently about this. And this is the power of science. That's the power of fundamental physics that I would like to share with you. And indeed, I mean, somehow our everyday life, it's very beautiful. And actually, this everyday life that we have, our understanding of what is surrounding us, it's made of very small component, which can be atom, molecule, or a little particle of light that we like to call photon. So those are the key ingredients, or as we like sometimes to say, building block of the reality. But then one could say, okay, those are the building block. That means that our reality and this building block follow the same rules. But actually it's not like this. While the reality around us is actually following classical physics, all these very tiny element is following other laws, which are the law of quantum mechanics. The word quantum mechanics was introduced about 100 years ago by, let's say, a group of physicists at the University of Göttingen. It's actually around the 1920s, and was meant to define the physics, the law governing small things, like atom, molecule, photon. But actually now, from 100 years ago to today, there have been a lot of discovery. So we start to understand what are these quantum mechanics, what is the implication. And actually, we now like to use a special sentence to show that now our understanding is getting a very high maturity, and we speak very recently about what is called the second quantum revolution. And what I would like to tell you is why after about 100 years, we are again in a quantum resolution. What does it change? The first revolution that was really the establishment of quantum mechanics was about understanding new law of nature. Now is about mastering, engineering, controlling, and make use of this new law. Okay, so a few years ago, prominent scientists, wrote all together a white paper showing indeed the opportunity of quantum mechanics and quantum physics. And just a few years after, the European Union decided that to call quantum technology as a disruptive new technology and considered to be a flagship of the, let's say, this new disrupting technology development. And since then, as a physicist, we are in the lab, we do fundamental science. I do fundamental science and not quantum technology, but I saw really a big change in my community because it started to become extremely interesting. And also suddenly there have been a seeding of money as support to the quantum technology. Over the last few years, I think we are now about 22 billion around the world. And also, I mean, there is a lot which go behind us about, let's say, geopolitical, let's say, allocation of support for this new quantum technology. Here you see an example of the number of patent filing in China comparison to US, and all this in the last, it's getting exponential increase over the last few years. There are many of these graphs you can find in internet, but what is my job is to try to give you the sense of why, or what is so powerful about quantum mechanics, and what is quantum actually. And that's what we want to do, and to do this, let's do a step back. So, and to go really back in time, so when actually the first concept of communicating, sending message over long distance was really introduced? Well, one key, development happened already in the 19th and 20th century. And actually the first very important, let's say, result was the discovery of electric and magnetic field and the description of this as wave. Now the wave, the electric wave or the magnetic wave, can be sent through very long distance. And actually in the height and the power, to simplify, of this wave, you might maybe even be able to encode signal. Okay, so light is transporting electric and magnetic field and can encode signal. This idea was then picked up by several scientists, and here I quote Guglielmo Marconi, that actually created the first long-distance radio transmission, which is the telegraph. Now, soon after, with a lot of effort, so together with the team and other scientists, this was the first transatlantic transmission. And then recently after, he also got the Nobel Prize together with Carl Ferdinand Braun for the development of wireless telegraphy. Okay, many years ago. And actually the idea here was to send message using wave. So just let's remember this: send message using wave, and the language of this message was what we all know, which is the Morse code. So let's say the point was to try to have two symbols. One is long, let's say this is long, and 1 is short, and to convert every letter of the alphabet and number in a sequence of these long, short, long, short, long, long, short, short. But this idea was then picked up by the binary logic that we use in our computer, because every of our computer is nothing else of a string, and that's the classical logic, of something which is 0, 1, 1, 0, 0, 1. So you see, there are 2 values, long, short, high, low, off, on, 0, 1. That's the binary logic. It's the classical logic. That's the one used in mobile phone, in your computer, in every type of calculator that you can have in several ways. Of course, the logic is very powerful. You encode complex information into a sequence of string of 0, 1. But then that's not enough. You have the logic, which means for me you have a language. We agree on a language, we do binary language, but we need to have something that is speaking this language. Well, in classical physics, this something, which has 2 logic levels, is the transistor. And actually, the first, what is called maybe to be one of the first computers is this Turing machine. Maybe some of you saw the movie, and actually it was used to crack the crypto system Enigma that was used by the German Reich during the Second World War. This was a gigantic, that's basically a first computer, which is basically a big calculator, which were with the aim of to crack the crypto system Enigma. And all this was speaking and make calculation based on 0, 1, 0, 1. And the object was not yet a transistor at the time. At the time was something very big called vacuum tube. Then, there was development, and the hardware was developed a lot, and really the transistors were invented. This is much smaller, you see, and this can very efficiently encode this logic 0, 1, 0, 1. Now, there was an additional strong development in technology, which was with the integrated circuit. And now you will have this small object with many transistors inside. And what is interesting is that there is an empirical law, which is called the Moore law, that tells you that while the years are progressing, the last year is 2020 in this graph, the number of transistors, so this object that is able to speak 0, 1, 0, 1, is kind of doubling every 2 years. That's a semi-log scale. Today, in a microchip, we have about 50 billion transistors. 1 second. We have, more transistor, more powerful computer. That's easy to understand. But actually, the computer is getting smaller. And what is actually the ultimate limit? How many transistors can we still put in something that is getting smaller and smaller? And that's interesting, actually, because the size of the initial vacuum tube in the Turing machine was, big as a penny. But now we are getting to transistor and integrated circuit, which are decreasing a lot their size, going almost at the size of a bacteria, and the ultimate limit to get, the size of an atom. And then you can ask how much energy you need to control one of these electronic devices, 0, 1, 0, 1. Well, the energy is reaching another regime, which will be enough to have 1 electron per device to activate 1 device. Okay, one moment. Now we have 1 atom, the size, 1 electron, the charge. We are again about the physics of tiny things. That's where quantum physics enter into play. And so we would say that let's say the watershed that were divided in this classical world to the quantum world is getting narrower and narrower. But let's see what is so special about the quantum world. Can it give us something more than a 0-1 transistor? Well, the first concept, which is maybe the most difficult in some sense, at least for me, to understand is how the energy of a single atom or a single electron is. Now, when we put, I'm Italian, so I used to do this example, we put water and we make boiling water, and when it's boiling, we put pasta inside, and the temperature of the water is continuously increasing. Okay, so there is a continuous increase of the temperature of your water. When the energy is quantized, this increase of energy, it's not anymore continuously, but jump from one level to the other level. If this is 1 electron volt and this is 2 electron volt, the atom cannot take any value in between the two. It's like a step function. That's the concept of quantization. And quantization also somehow protects the level, the energy level of an atom, because it's not so easy to get if nothing happens from here to down. So there is this quantization which actually defines very clearly a discrete number of value that the energy can take. It's not continuous. That's a big difference. And it's a big difference also because if this is the case, I know where exactly what the energy level of my atom, I can even use laser light or photon that we said before. And by giving this laser light, I can promote my atom in an excited state. Okay, I have two levels. One is down, one is up. I have 0, 1. I'm getting back to the idea that I have two very distinct states of an object, and this is just an atom having it. And so far you might think, okay, fine, it's a transistor, instead of being an electric circuit, it's just an atom. Okay, you will encode a very long string of 0, 1, that's over, but actually there is much more. Because, and here is the craziness coming up, because the state of your atom can be at the same time in 0 and in 1. This is one of the key principles of quantum mechanics, which is called superposition principle. So before you make any measurement, the atom can be at the same time down and up. That's why we speak about this Schrödinger cat, which is at the same time dead and alive. It's at the same time two different things. And these have a lot of power, because now, let's say the state don't have to take only 0 and 1, can take many more value. And actually, related to the key foundation of quantum mechanics, there was the Nobel Prize of last year given to Zeilinger, Clauser, and Aspect for the entanglement in principle. So somehow, let's say, to put it in more simple means, when you have two doors, in our classical world, there are decisions that we need to take. Either we go to the right door or we go to the left door. But if we are in the quantum world, actually, you don't have to take any decision. You could pass simultaneously in both doors. And now you might think that I'm crazy, that all this is just an oddity, that's just mathematical, that it's not happening. But actually, you can really do experiment. You can really send, let's say, some flux of light in two doors, and you can really see outside on the screen that they are passing everywhere at the same time. And you can even do this with atom or electron. This is the so-called double slit experiment, where you see in the screen that there is a probability to pass in both. And so this is a very powerful concept, but now come an additional little difficulties. So what you need to, let's say our world is deterministic. Either you go to the right door or to the left door. The quantum world doesn't need this definition. It's not important. When you start to measure, it's becoming important. Before you measure, you are in this superposition state. So now this state is in a superposition of 0 and 1. Then you are measuring, and you get only projected in one of the states with a given probability. Or you do again the measurement, and you are projected in another state with another given probability. So in total, you can have much more value because of the probability that's simply 0 and 1. So somehow, to make it an idea, while the classical bit is taking 0 and 1, the qubit can take all the value between 0, 1, 0, 0.1, 0.001, 0.2, and so on. And this is extremely efficiency, to the point that in theory, let's say if you think about 64 qubit and all possible states, this would be equivalent to the number of states you have with 10 to the T-classical bit. So this is an extremely important change, and actually it's called in some cases quantum supremacy. Now the problem where we are today is to find, we have found the language. The language seems very powerful. This qubit, let's say this superposition principle, it seems very, very powerful. And the question is, what is the object able to speak this quantum logic? So what is the quantum transistor? And actually, this is where there is today the technological race, to find the proper object that speak quantum physics. There are several companies around the world, a very big one, a lot of research group, but I think there is not yet, a clear identification of what would be the hardware here. Now, I told you about one atom, how powerful it is, the idea that the energy levels are quantized, that one possible application of this is really to create this qubit, but there is also much more. Let's abandon the qubit, and let's see what more this quantized level can give it to us. So another thing that it can give it to us is that you can make the atom, oscillating between two levels. This oscillation is like a pendulum. And this oscillation is like to have a clock. We call this atomic clock. It's the most precise way to define second. It's the most precise measurement of time, is the oscillation between two energy levels of an atom. Then first, the second was defined in terms of cesium. Now there is a new redefinition of second going on. But the key point is that this precision of atomic clock is essential to make the GPS in your mobile phone to work. Because the GPS needs to know the space and the time. And for the time, you need a clock, which is an atomic clock. Another example, which I also like to give, is that now you have these two energy levels, but the distance between these two levels is not fixed. Actually, if you have a magnetic field around, even a very small magnetic field, this distance of the energy can change. It's an energy difference. So if you have a magnetic field around you and you measure this energy difference between A1 and A2, you can immediately measure the magnetic field. Why it's relevant? Well, it's relevant in many applications. Even, let's say, thinking about the brain. So when a neuron is activated, it's creating a tiny magnetic field. And actually, an atom or something similar to an atom can be a sensor for the magnetic field or for the, let's say, anomalies in the magnetic field distribution of your brain, because it's a sensor with an exquisite capacity to measure very tiny magnetic field. In my lab, if I look at my atom, I can tell you where the elevator of the building is. Because an elevator, when it moves, creates magnetic field. And my atoms are sensors. That's not very nice effect. We need to compensate. But just to give the sense that one atom can really measure very small magnetic field. And what happens if you don't have one, but you have many atoms, many more atoms, and each atom are, interacting between each other. Here you enter from, let's say, the single quantum object to what is called many-body quantum physics, which is actually my field of research. And the first things that you need to think about is that for our field of research, there is something that we don't like. And what we don't like is temperature. Because for us, if the atoms are hot and they move, this is really a noise that it's masking all the quantum phenomena. So the first thing we need to do is to cool down enormously the temperature and go to very close to zero temperature. Now, cooling down doesn't mean to stop the motion of an atom. But it means to make a strange transition into what it's called the wave-particle duality. When we decrease temperature, if each of these atoms start to behave as a wave. And this is another craziness of quantum physics. The atoms start to have the probability like a wave. That's really matter. Object has a weight. and start to be delocalized as a wave. There is a probability to find atom in various places of the space. And smaller is the temperature, longer is the wave. Up to some point in which all this wave made of matter will interfere and create what is called a Bose-Einstein condensate, which is a gigantic wave, all following macroscopically the law of quantum mechanics, which actually have been discovered already about 20 years ago. But now you might ask me, okay, how cold we should be, actually. And we need to be pretty cold. And now to give you a sense, those 2 points on this temperature scale, that's like our thermometer, the coldest place in the Earth and the hottest place in the Earth, in my scale, are almost the same point. Okay? Then the temperature is just of the sun surface is just a bit far away, and if you think about the coldest space in the universe, this background cosmic radiation is also here nearby, and here is the very intense collision between particles, and we are here with ultra-cold atom. And now let me show you how it is. So you have, this is a video, you have atom going in one direction, and then this blue light is what we use to slow down the motion. We use light and what is called laser cooling to slow down the motion of our atom. And all the atoms are now getting, in some region here captured. And here is where the final part of cooling is happening, and we are preparing our gas at this very, very, very low temperature here. Okay, that's, of course, a video. And the first time that the Bose-Einstein condensate was observed was in June 95. And this is with a specific atom called rubidium, and you see the appearance of this huge peak, which is indicate that there is this kind of interference of wave. And then it was predicted by Bose and Einstein, and then many, many years later, thanks also to the development of technology, was created. And the type of atom that we have, that's how the lab look like. That's our lab in Innsbruck. A lot of light, a lot of mirror. And actually in Innsbruck, what we use is specific atoms which are strongly magnetic. Now, I just want to give you one example of what can be done with this magnetic atom and then close. Actually, we are used to think that matter have 3 states. You can have things around you which are solid or liquid or in gas phase. But it's also possible to have new type of state of matter that escape completely this type of classification. It's a little bit, and in our case, it's a gas. I told you a condensate is a gas, which have both properties of being a solid and a liquid. And because of all this special property, this is called the supersolid state. It's a little bit like the Schrödinger cat, that it's alive and dead, but here we have a state that is simultaneously fluid and crystal. And actually, it was not very clear that this state was existing. There are very prominent scientists very convinced that it was impossible to create a state which is both solid and liquid at the same time. And others that said, no, it's possible, quantum mechanics allow this type of state. And all of 4 got the Nobel Prize, so it was a very high-level discussion between them. And at the end, there were several thoughts on how to realize this type of state. And a few years ago, my group and the group in Italy and another one in Germany realized with the gas, the first state, which is supersolid, each, you see, is a gas, but all atoms, are independently organizing in a very, order phase, while keeping global phase coherence, and you can really, cool down the system and get this new type of state and even go, let's say, to 2 dimensions. And this is just an example of what we can do if we have many, many particles, and to give you a flavor of how many discoveries there will be. And I would like to conclude now my talk with, again, a sentence. We started with the sentence. Let's close with the sentence. which say the scientific person does not aim at an immediate result. Actually, his or her duty is to lay at the foundation of those who are to come and point the way. I'm sure that the founding father of quantum mechanics never thought that we would go so far with understanding this new field of research. And with this, I would like also to present my team in Innsbruck and to also say thanks to the fantastic team that, were in this journey with me. Thanks. Oh, okay. So we have time for 2 questions in case you want to try out. There is a, yes.
And first of all, thanks for this amazing talk. I really enjoyed this walk through the work.
Oh, thank you.
And my question is just out of curiosity, in the last part where you show us this video where you cool down the atoms with the laser cooling, then they stop in this orange intersection. What were those orange thingies?
Yes, we do actually, thanks a lot for this nice question. We do everything with light. So on the one hand, light can be used to stop the motion of the particle, and so that means to cool down the particle if they have the right color, okay? And then we can, we have the beam and we stop the beam, but at the same time the light can be used to simply trap. If, the light has not the right color, you can use this light to create any sort of trap. Like, for example, also to create crystal of light where you would put a single atom in every crystal side. Quantum simulate properties of material, solid state physics, and this type of things. Thank you.
Thanks.
I don't know if there is another question. Yeah.
Could you give us some hint of what's the difference between a superfluid and this supersolid phenomenon?
Yes. Okay. So the supersolid is a state which is superfluid. Okay, so it's a special class, but it's a class in which the atoms that are indistinguishable and compose the system not only have agreed among themselves that they have to be coherent, have only one phase, but they also agree among themselves where to be in space. So they kind of break the translational symmetry and create this wave like a crystal, so a periodic structure in space. So they have both, but since they are indistinguishable, you cannot say which particle is actually flowing and which one is localized in the supersolid. And these things that you cannot say, that they are simultaneously with both properties, make the state, let's say, uncuttable. You cannot cut the solid part and remain with the other. They are highly correlated.
Thanks.
Okay, so thank you very much for your time.